got breaking news here of a fantastic chemical discovery called NMR. And NMR is when a molecule is spinning, there's a magnetic field, and when a radio wave is shot into that molecule, it helps us to see differences in carbon and protons.
In C13 NMR, we see chemical shift and unique carbons. In proton NMR, we see unique protons, chemical shift, integration, and coupling. Now we go to Professor DeMattean to show us how it's done.
So let's take a look at a simple example here of a proton NMR graph. We mentioned that integration is present on proton NMR, which shows how many protons are a part of this molecule. And here we see two H's, which means that it's two identical protons. And then our coupling shows how many neighboring protons there are plus one. So we've got two neighboring protons plus one, shows that in this case there's a triplet. And we know here because of that we're probably going to have a carbon that's going to have two protons attached to it. Those are identical protons. And we've got another carbon here that's going to have probably two protons branched off to something else. And then because it's showing up so far downfield, we can be pretty confident that there's going to be a heteroatom involved in this structure. Here we see that we've got three identical protons in just a single peak here. So we're going to have a carbon down to three hydrogens with zero neighboring protons. And because it's downfield, we can be confident that that's going to be due to this heteroatom here. Moving on down this graph, we see that we've got two identical protons. We've got 6 peaks, which shows 5 neighboring hydrogens. And so if we're to draw that out, we can be confident that this is probably in the middle of a molecule. So we've got our two identical carbons. Here's a carbon with 3 hydrogens coming off to create 3 neighbors. Then we can have another carbon with 2 more neighbors. And that's 5 neighbors plus 1 gives us our 6 peaks and our 2 identical protons here. And our last peak here on the graph shows 3 identical carbons, and it's got 2 neighbors plus 1 gives us a triplet. So we've got a carbon that's going to have 3 hydrogens attached to 1 more carbon, and then that can have 2 hydrogens here with our 3 identical protons.
Now we're going to look at a C13 NMR and a proton NMR combined. As we look down at these two bonds, we're going to see that they're both CH3 bonds because they're super upfield. And this bond is going to be attached to an electronegative atom because it's just a little bit above this one. So we're going to assume that that one is attached to a carbon or an oxygen atom. This one, because it's more downfield, it's going to be attached to the chlorine because chlorine is more electronegative than this oxygen. So it is a CZ bond as well. This bond here is going to be our carbonyl group, which is double bonded in oxygen. We have the other oxygen here, which is going to be there, and a carbon. As we look down at the proton NMR, this will not show up on the proton NMR because there are no protons. So we're going to go ahead, we're going to draw that out here, have the oxygen here. As we look at this first peak, we see that it's a 3-peaked bond, or has 2 neighboring hydrogens plus 1. So we know that that's going to be a CH3 group. We're going to draw that over here. And then we have this peak that is also, it's going to be a CH2 plus 1, so we've got the 2 hydrogens, and these two are the same except this one is attached to a more electronegative atom because it's more downfield. So we're going to go ahead, we're going to draw this is going to be the CH2 here, and because it's right here, it's going to be attached to another carbon. This peak is going to be attached to an electronegative atom, and that's going to be the chlorine atom. So we're going to draw the H2 here with the chlorine, which gives us these neighbors here, these 2 neighbors, as we can tell. Now right here, this quartet peak, that's going to be a carbon attached to this oxygen, and then we have a hydrogen, and then a carbon. So we get the quartet here with these neighboring hydrogens here. And because it's more downfield, it's attached to this oxygen, which does that for it.
Thank you, Professor DeMattean.